This arrangement does not comply with the National Electrical Code. Article 210.4 requires that branch circuits be supplied from a single circuit breaker or fuse. In this case, the branch circuit supplying the security lights is being supplied by two circuit breakers, a 15-amp 2-pole breaker in the 400-amp panel and a lighting contactor. Article 210.4b requires that branch circuits be protected in accordance with their ampacity. In this case, the 15-amp 2-pole breaker is protecting a circuit that includes four 400-watt luminaires and 12 70-watt luminaires. The total load on this circuit is 4 times 400 watts plus 12 times 70 watts, equaling 1960 watts, which exceeds the 15-amp rating of the breaker. To correct this violation, firstly, install a separate circuit breaker or fuse for each branch circuit. Secondly, ensure that the circuit breakers or fuses are rated for the ampacity of the circuit. Let's delve deeper into these NEC violations and how to rectify them, providing a comprehensive understanding of the underlying principles. We'll begin with Article 210.4a, which is fundamental to branch circuit design. This section mandates that each branch circuit must originate from a single overcurrent protective device, such as a circuit breaker or a fuse. The purpose of this requirement is to ensure that the entire branch circuit can be energized by a single action, providing a safe and reliable means of disconnecting the circuit for maintenance or in the event of a fault. In the described scenario, the security lights are fed through both a 15-amp 2-pole breaker and a lighting contactor. This arrangement violates Article 210.4 because the circuit is effectively controlled by two separate devices. If a fault occurs downstream of the terminal blocks, neither the breaker nor the contactor alone can guarantee complete isolation of the faulted section. The proper approach is to have each branch circuit supplying the security lights originate directly from a dedicated circuit breaker in the 400-amp panel. This ensures that a single breaker controls and protects each individual circuit. Now let's examine Article 210.4b, which addresses the critical aspect of overcurrent protection. This section stipulates that branch circuits must be protected in accordance with their ampacity. Ampacity refers to the maximum current in amps that a conductor can carry continuously under specified conditions of use without exceeding its temperature rating. The overcurrent protective device, such as a circuit breaker or fuse, must be selected to protect the conductors from overload and short circuit conditions. In the described installation, the 15-amp 2-pole breaker is tasked with protecting a circuit that feeds both four 400-watt luminaires and 12 70-watt luminaires. To determine if this arrangement complies with Article 210.4b, we must calculate the total load on the circuit and compare it to the breaker's rating. As previously calculated, the total load is 1960 watts. However, to properly assess the load, we need to convert watts to amps using the formula amps equals watts divided by volts. For the 480 volt portion of the circuit, the four 400-watt luminaires draw a current of 4 times 400 watts divided by 480 volts, which equals approximately 3.33 amps. For the 277 volt portion of the circuit, the 12 70-watt luminaires draw a current of 12 times 70 watts divided by 277 volts, which equals approximately 3.3 amps. Therefore, the total current draw on the circuit is approximately 3.33 amps plus 3.3 amps, which equals 6.36 amps. While this is lower than the 15-amp breaker rating, we must consider other factors, such as the continuous nature of the load and the potential for increased current draw due to voltage fluctuations or component aging. Moreover, the NEC requires that overcurrent devices be sized no larger than the ampacity of the conductors they protect. Therefore, it is essential to select conductors with an ampacity sufficient to carry the calculated load, plus any applicable directing factors. To correct the violation of Article 210.4b, it is necessary to install separate circuit breakers for each branch circuit, ensuring that the breakers are appropriately sized for the ampacity of the circuits they protect. For example, a separate 15-amp breaker could be used for the 480-volt circuit feeding the four 400-watt luminaires, and another 15-amp breaker could be used for the 277-volt circuit feeding the 1270-watt luminaires. This approach ensures that each circuit is individually protected against overloads and short circuits, enhancing the safety and reliability of the electrical system. In addition to addressing Articles 210.4 and 210.4b, it is also important to consider other relevant NEC requirements, such as those pertaining to conductor sizing, overcurrent protection, and wiring methods. Conductors must be sized in accordance with their ampacity and any applicable dirting factors, as specified in NEC Table 310.15. Overcurrent protection must be provided in accordance with the conductor's ampacity and the requirements of Article 240. Wiring methods must comply with the provisions of Chapter 3 of the NEC, which covers various types of wiring systems, including conduit, cable, and raceway. By adhering to these comprehensive NEC requirements, it is possible to design and install a safe and compliant electrical system for the high school football field lighting. This will not only protect the electrical equipment from damage but also safeguard the lives of those who use and maintain the system. Furthermore, compliance with the NEC can help to prevent electrical fires and other hazards, ensuring the overall safety and well-being of the community. In summary, the described installation violates both Article 210.4 and Article 210.4b of the National Electrical Code. To correct these violations, it is necessary to install separate circuit breakers for each branch circuit, ensuring that the breakers are appropriately sized for the ampacity of the circuits they protect. Additionally, it is important to consider other relevant NEC requirements, such as those pertaining to conductor sizing, overcurrent protection, and wiring methods. By following these guidelines, it is possible to create a safe and compliant electrical system for the high school football field lighting, protecting both equipment and people from electrical hazards. Let's consider some additional aspects of this electrical installation to ensure a comprehensive understanding and compliance with the NEC. Firstly, grounding and bonding are crucial for electrical safety. The NEC Article 250 covers grounding and bonding requirements, which aim to create a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices and minimizing the risk of electric shock. Ensure that the grounding electrode system is properly installed and connected to the service equipment. This typically involves grounding electrodes such as ground rods, ground rings, or metal underground water pipes. The equipment grounding conductors must be properly sized and connected to all non-current carrying metal parts of the electrical system, including enclosures, raceways, and equipment frames. Secondly, surge protection is an important consideration, especially for outdoor lighting systems that are exposed to lightning and other transient voltage surges. The NEC Article 280 covers surge protection devices, which are designed to protect sensitive electronic equipment from damage caused by voltage surges. Consider installing surge protective devices at the service entrance and at the lighting contactor to mitigate the risk of surge-related damage to the luminaires and other electrical components. Thirdly, control wiring for the lighting contactor must comply with the NEC requirements for Class 1, Class 2, or Class 3 circuits as applicable. The NEC Chapter 7 covers special conditions, including control circuits. Ensure that the control wiring is properly insulated, protected from physical damage, and separated from power conductors. The control circuit overcurrent protection must be sized in accordance with the ampacity of the control conductors. Fourthly, wiring methods for outdoor lighting must be suitable for wet locations and protected from physical damage. The NEC Article 300 covers wiring methods. Consider using rigid metal conduit, intermediate metal conduit, or liquid-tight flexible metal conduit for outdoor wiring. Direct burial cables must be listed for direct burial use and installed at the proper depth. Fifthly, accessibility and working space around electrical equipment must comply with the NEC requirements. The NEC Article 110 covers general requirements for electrical installations, including accessibility and working space. Ensure that the 400 amp panel and the lighting contactor are readily accessible and that sufficient working space is provided around the equipment for safe maintenance and repair. Sixthly, documentation and labeling are essential for proper operation and maintenance of the electrical system. Provide clear and accurate documentation, including panel schedules, wiring diagrams, and equipment specifications. Label all circuit breakers, switches, and other electrical components to identify their function. Seventhly, energy efficiency should be considered when selecting and installing lighting equipment. The NEC does not mandate specific energy efficiency requirements, but it does reference standards and codes that promote energy conservation, such as the NEC International Energy Conservation Code. Consider using high-efficiency luminaires, such as LED fixtures, and implementing lighting controls, such as occupancy sensors and dimmers, to reduce energy consumption. Eighthly, future expansion should be taken into account when designing the electrical system. Consider installing spare capacity in the panel board and raceways to accommodate future lighting additions or modifications. This will minimize the need for costly and disruptive upgrades in the future. Ninthly, coordination with other trades is essential for a successful project. Coordinate with the general contractor, architect, and other subcontractors to ensure that the electrical installation is properly integrated with other building systems. Tenthly, compliance with local codes and regulations is mandatory. Check with the local electrical inspector and building department to determine any specific requirements that may apply to the project. Ensure that all electrical work is performed by qualified and licensed electricians. By addressing these additional aspects of the electrical installation, you can ensure a comprehensive and compliant system that meets the needs of the high school football field lighting. This will not only protect the equipment and people from electrical hazards, but also provide a reliable and efficient lighting system for years to come. Furthermore, regular inspections and maintenance are crucial for maintaining the safety and reliability of the electrical system. Schedule periodic inspections by a qualified electrician to identify and address any potential problems before they become serious. Perform routine maintenance tasks such as tightening connections, cleaning equipment, and replacing worn components. Keep accurate records of all inspections and maintenance activities. In conclusion, electrical safety is paramount, and compliance with the National Electrical Code is essential for protecting people and property from electrical hazards. By understanding and adhering to the NEC requirements, you can create a safe, reliable, and efficient electrical system for any application. Remember to always consult with a qualified electrician for any electrical work, and never attempt to perform electrical work yourself unless you are properly trained and licensed.